Hello, it's stat134, lecture 32, and last time we covered section 5.3, independent normal variables, and we used the MGF to prove that a linear combination of independent normals is normal. And we showed that if x1 to xn are IID standard normals, then the sum of their squares is a gamma. R is n over 2, lambda is a half, which is called a chi-square distribution with n degrees of freedom, written chi-squared sub n. And the n is because we have n independent standard normals. So then we talked about the convolution formula for the density of a sum. So remember, if x and y are random variables and we write S to be their sum, the convolution formula gives us a formula for the density. If x and y are positive random variables, essentially what we're doing is integrating out the x, and if x and y are independent, then the joint density factors. So more generally, we integrate from x's minus infinity to x's infinity. So today we're going to go over student comments from the concept test from last time. Then we're going to finish 5.4. So next time we'll be starting our last chapter, chapter 6. So we'll also show an example from the book where x, y are IID standard uniform, and S is the sum of x and y, and we'll find the density for F. It's called the triangular density. And we'll introduce the convolution formula for the ratio of two random variables. And finally, we'll prove that what I showed you as the density for the beta actually is a density. It does integrate to 1. So lots to do today. So we started, we recall the concept test that we had last time. And so I gave you guys a moment to remember your work on this and the solution. So if y is standard normal, then 2y is normal 0, 4, and x minus 2y is normal 0, 5. So the probability that x is greater than 2y is the probability that x minus 2y is greater than 0. We can normalize both sides, and we get the probability that z is greater than 0, which is 1 minus phi of 0, which is a half. And so some students write, because the sum 2y minus x is normal 0, 3, which is still symmetric about 0. That's great, except that it's normal 0, 5. I actually made that same mistake. Wait, the image is symmetric on the plane. Yes, indeed, it is. And so here I've attempted to draw the image they're talking about here, which is 0, 5. The image is, let's see, so it's the area, so it's the area for x greater than 2y. So that's the area under the line y equals 1/2 x, and yeah, that is half the plane. So another person wrote yesterday and pointed out that in fact it's not n03, it's n05, thanks to that person. And another person wrote basically my solution: z is x minus 2y is normal 0, 5, so the probability that z is greater than 0 is 1 minus phi 0. That's not how you spell phi, though. And one person mistook normal 0, 1 to be uniform 0, 1, in which case definitely the probability that x is greater than 2y is not a half. Great work. So next we look at the density for the sum of two IID standard uniforms. And here, note that the probability that S is in ds, so that as S runs from 0 to 2, that needs to sum to 1. And you can see that when S is between 0 and 1, that the probability for S to be in ds increases. In fact, it increases linearly. And once it reaches its max value when S is 1, and then it decreases in a symmetric way back down to 0. Now the probability that S is ds is Fs ds. ds is just a constant, is always the same. So Fs is in fact increasing linearly, and we'll show that it is this triangular density shown here. So for S between 0 and 1, you can just use the convolution formula to see that Fs is in fact just S, so that's between 0 and 1. And for S between 1 and 2, if I note that X and Y being IID uniform 0, 1, then 1 minus X and 1 minus Y are IID uniform 0, 1. And T, if I let T be 2 minus S, that's 1 minus X plus 1 minus Y. T is between 0 and 1, and I can use the convolution formula for T and show just in exactly the same way as above that Ft is T, and then the change of variable formula gives me Fs for S between 1 and 2 to be 2 minus S. So now we do the convolution formula for the density of the ratio y over x. So here x and y, let's say, are greater than 0. Z is y over x. So the picture we have is as follows. So we can interpret z as the slope. The slope of the line y equals zx, and right, so the probability that z is in dz is this light shaded green region, and the probability that z is in dz and x is in dx is this darker shaded region here. I'm sorry, so the probability that z is in dz is the volume under the joint distribution above the light shaded region, and similarly for the probability that z is in dz, x is in dx. If you just want to think about the probability that z and dz is the light shaded region, we'd need the joint distribution to just be 1. But that's not generally the case. Okay, and so the important thing here to note is that what I call delta y here, that's z plus dz times x minus zx. That is equal to x dz. So the area of that small parallelogram, or it's actually not a parallelogram, it's just a region. The dark shaded region there is area delta y times dx. So in other words, x dz dx is the area. So we just multiply that times the height of the function, the joint distribution at x zx. So there you go. So the probability that z is in dz is the integral from 0 to infinity of the probability that z is in dz, x is in dx, which is the integral shown below. And now f of z, we just remove the dz term, and we get the convolution formula highlighted below. So then I gave you guys a problem to practice, just recalling that what the density of a gamma is, and this identity boxed here. So let x and y be IID exponential 1, z be the ratio of y over x, find the density of z. And so you did this, and if you recognized a gamma r is 2 lambda 1 plus z, that everything went very smoothly for you, and you get 1 over 1 plus z quantity squared. Then we did a concept test, and a lot of you did a great job on this. So you sort of need to, so we're looking here at the case where y is between 0 and 1. So using my convolution formula, it's easy to see that I just get a half here for y between 0 and 1. The follow-up problem, we had y greater than 1, and hence I need yv to be less than 1, because that's where my density for u is non-zero. And so, in other words, v has to be less than 1 over y. So, and that's achieved when y is greater than 1. So I'm integrating from v is 0 to v is 1 over y, and you carry out the integral and you get 1 over 2y squared for y greater than 1. Finally, we showed a clever argument that the formula for the density of beta is in fact a density. It does integrate to 1. So we used quite a clever argument involving gamma and the convolution formula. So we're going to have x and y be independent gammas with the same lambda, and so I write out the convolution formula for z, and what the convolution formula does for me is it assures me that fz is a density, because that's what the convolution formula does. So the thing on the left is a density, and just follow each step. We make a change of limit of integration to introduce a variable p between 0 and 1. Notice that z is greater than x, because z is x plus y, where x and y are positive. So p takes values between 0 and 1. And making this change of variable here, we will recognize that, oh my gosh, we're getting the beta, the variable part of beta here. And so rearranging things here, recognize the variable part for f of z is gamma r plus s lambda, and writing the constant part in a funny way here. We get exactly the density for gamma inside the convolution density, and hence the quantity, the constant in the yellow bracket here must be 1, and that is nothing else than the integral of the density of beta. So that proves that what we gave as a density for beta in fact does integrate to 1. So that was the show for today. We're going to start chapter 6 next time. Have a great day.